Most of the earthquakes recorded in the world aren't very strong, but sometimes a particularly great one causes destruction and death. Earthquakes also occur at the sea bottom. When that happens, they can sometimes displace the water column and originate waves. These waves are best known by their Japanese name, tsunami, which simply means harbor wave. Regular sea waves caused by the wind are very different from tsunami waves. Let's find out why. Wind blowing over the sea can only move the upper layer of water, forming waves but not affecting movements deeper down. The water particles near the surface move with a circular motion, which helps to propagate the wave along. Deep down, the water particles don't move. The strength with which these waves reach the coastline depends exclusively on the movement in the first few meters of water. A tsunami, on the other hand, can be generated at the bottom of the sea. In case of a strong earthquake, the sea floor abruptly deforms and vertically displaces the overlying water. The entire water column is disturbed by the uplift or subsidence of the sea floor. This sudden movement releases a great impulse of energy, which is transferred to the whole column of water between the surface and the sea floor. In this case, the water deep down moves as well, as deep as 1,000, 2,000, 3,000 meters. Apart from submarine earthquakes, tsunami waves can also be generated by underwater landslides, or when rocks or sediments slide into the sea, by volcanic eruptions, or more rarely, when a meteorite falls into the sea. Alarm systems currently in use in the Pacific and Indian Oceans give advance warning when a tsunami is generated. These systems rely on sensors placed at the sea bottom, which measure variations in the water above and transmit an alarm via floating buoys and satellite link-ups with observation stations on the coast. Once generated, tsunami waves in the open sea travel very, very fast, up to 800 kilometers per hour. They can cover thousands of kilometers and approach coast far from their point of origin with great energy. In the open sea, the waves are rarely over a meter high and are very long, so they're imperceptible. A ship in open sea, for instance, wouldn't notice anything out of the ordinary. The speed of a tsunami wave depends on the depth of the water the wave is traveling through. Approaching the shore, the tsunami's speed diminishes, although it's still much, much faster than an ordinary wave. Also, wave amplitudes will increase dramatically. This is due to the fact that the tsunami's energy flux, which is dependent on both its wave speed and wave height, remains nearly constant. Consequently, as the tsunami's speed diminishes as it travels into shallower water, its height grows. This huge and fast-moving mass of water shifts an entire column of water from the sea floor to the surface. Approaching the coast with a destructive force far superior to any wind-generated wave, it can advance hundreds of meters inland. That's why, even if it isn't very high, a tsunami wave can still cause serious damage along a coastline. When the trough of the wave first reaches the coast, the tsunami appears to make the sea withdraw, often quite consistently, leaving harbors and beaches dry. This can last for several minutes and is a sign to get as far away from the shore as quickly as possible. The crest of the wave will arrive at any minute. It may look like a sudden high tide that keeps getting higher, or a wall of water moving faster than any normal wave. It carries with it the energy of the earthquake, not that of the wind.